This is continuity of our discussion on complex functions. So far, we have defined what are complex functions. So a complex function is the rule with the help of which each complex number from the domain is assigned to a unique complex number. Now, if we want to do calculations with complex functions, for example, if I want to calculate what are the images under some function of a complex number, or if I want to explore further properties, the continuity, limit, derivatives, and other properties of complex function, then we need to have some very precise descriptions of these complex functions. Now we know that any complex number can be written as x plus iota y, where x and y are real numbers and iota is square root of -1. So when we apply function on a complex number x plus iota y, then we get another complex number, let's say u plus iota v. So we can say that the complex number can be written in the following form. So f applied on this x plus iota y is equal to u plus iota v. Now the point is, whenever I change x and y, the values of u and v will be changed. So we can say that these u and v's are in fact functions of x and y. So we can write down the function in the following form: u of xy, because this u varies when you change the values of x and y, and similarly the v varies as we change the values of x and y. So we can say that a complex function is basically w is equal to f of z is equal to u of xy plus iota v of xy. Now here once again, this u and v are real valued functions, and the input of this function is basically x and y. Now let's consider in particular a function conjugate of z multiplied by real value of z plus z square plus imaginary part of z. Now let's try to write down this function in the form u of xy plus iota v of xy. Now in the first step, we write down the values of z conjugate. The real value, the real part of z is basically x, and z square, in other words x plus iota y square, plus the imaginary part of z, which is y. And we can simplify this thing. So opening this square, we get x square plus iota square y square. Now iota square is -1 plus 2 iota xy plus y. And simplifying further, we get 2x square minus y square plus y plus iota xy. Now this is the real part of the output. So in other words, we can say this is u of xy, and this is the imaginary part. So we can say that this is v of xy. So that's how we can write down this function as u of xy plus iota v of xy. Now conversely, if we are given a function in the form u of xy plus iota v of xy, then we can write it down as a function involving only variables z and z conjugate. So how to do that? So for that, we need to observe that x is equal to z plus conjugate of z divided by 2, and y is equal to z minus conjugate of z divided by 2 iota. Now it is very simple to see why this is true, because if z is equal to x plus iota y, then conjugate of z is basically x minus iota y. Now if we add them, so z plus conjugate of z becomes 2x, and iota y will be cancelled out. So this implies that x is equal to z plus z conjugate divided by 2. Similarly, we can observe that y is equal to z minus conjugate of z divided by 2 iota. Now using these two expressions, we can convert any function which is given in the form u plus iota v. We can convert it into a function involving only variable z and z conjugate. So how to do that? Let's consider another example where we have function given in the form 4x square plus iota 4y square. Now of course here u of xy is 4x square and v of xy is 4y square. How to write down this function in terms of a function that involves only z and z conjugate? So for that the idea is very simple. Just use the value of x is equal to z plus z conjugate by 2. So if it's 4x square, so it becomes 4. So replace x with z plus z bar divided by 2 square plus iota, and replace this y with z minus z conjugate divided by 2 iota. Now in the next step we can just simplify it. So simplifying them, so this 4 will be cancelled out this 2, and this 4 will be cancelled out this 2 square, and simplifying further we get this expression. Hence the function was given in the form u of xy plus iota v of xy, and we converted it into a function f of z. Of course it is the same function, but the form is now different. Now the form of the function involves only z and z conjugate. Now there is a very special kind of function where the imaginary part in u plus iota v is 0. Of course if the imaginary part is 0, then the output is a real number. So one such example of such function is where we calculate modulus of these complex numbers. So in other words, the function is given as f of z is equal to modulus of z, or the absolute value of z. So it is one of the important functions in our further discussions. Now we know that a complex number can be written in the Cartesian form x plus iota y, and it can also be written in polar form, and in particular it can be written as r into e raised to power iota theta, where theta is the argument and r is the modulus. Now if we have this form of the complex number, then what will be its effect on the form of complex valued function? Now if we are given a complex valued function w is equal to f of z, then replacing z is equal to r e raised to power iota theta, so this gives us u of r theta plus iota v of r theta. Of course the output of this complex valued function is a complex number. Now this time our u and v does not depend on, of course, x and y. They depend on r and theta, because the input is in the form of r and theta, and as you vary the values of r and theta, the output will be varying. So in other words, in this case u and v are functions of r and theta. Now let's have a look at some example. So if f of z is equal to z square, now can we convert, using the polar form of complex number, can we convert this function into u of r theta plus iota v of r theta? Of course in this case the answer is very simple, because you just replace z is equal to r e raised to power iota theta in the value of f of z. So in other words, if f of z is equal to z square, then just replace z is equal to r e raised to power iota theta here. So it becomes r e raised to power iota theta is equal to r e raised to power iota theta square, and this becomes r square and e raised to power iota 2 theta. Now we can expand this thing, because we want to know what are the real and imaginary parts of this complex function. So we want to expand this e raised to power iota 2 theta. So it becomes cosine 2 theta plus iota sine 2 theta. So multiplying this r square cosine 2 theta. Now this is the real part of this complex valued function, plus iota r square sine 2 theta, and this is the imaginary part of this function. So we have this u and we have this v. So what is the value of u? R square cosine 2 theta. And what is the value of v? R square sine 2 theta. Now using polar form of complex number, we have calculated what are the real and imaginary parts of a complex valued function. Now if we are given a complex valued function, we want to know using Cartesian coordinates and polar coordinates what are the real and imaginary parts of this complex valued function. Now first consider this function f of z is equal to z square plus z plus 1. Now we want to calculate both real and imaginary parts using the Cartesian coordinates and the polar coordinates. Now let's first calculate in the case of Cartesian coordinates. So of course in this case we replace z is equal to x plus iota y. So just replace the value of z is equal to x plus iota y in here. So we get x plus iota y square plus x plus iota y plus 1. Now expanding this square, we get the following expression plus x plus iota y plus 1. Now we can collect the real numbers and imaginary numbers, in other words in numbers which are multiples iota separately. So this becomes the real part and this becomes the imaginary part. So in other words, our u is equal to x square minus y square plus x plus 1, and our imaginary part of the function v of xy is 2xy plus y. Now let's calculate in the case of polar coordinates. So in this case, of course, we are going to use the following form: z is equal to r e raised to power iota theta. So replace this value of z in f of z. Okay, so in other words, f of z is equal to f of r e raised to power iota theta. So in other words, this becomes r e raised to power iota theta square plus r e raised to power iota theta plus 1. So in other words, we have this form. Now expanding this thing, we get this thing. Now when we take square of e raised to power iota theta, we get e raised to power iota 2 theta. Now expand that and we will get cosine 2 theta plus sine 2 theta, and then multiplying them with r square, we get this form. And similarly, we can expand r e raised to power iota theta plus 1. Now collecting the real and imaginary numbers separately. So this is the real part and this is the imaginary part. Okay, so in this case, u of r theta is r square cosine 2 theta plus r cosine theta plus 1, and v of r theta is equal to r square sine 2 theta plus r sine theta. Now in this example, we have considered the same function and we calculated u and v in the case of Cartesian coordinates and in the case of polar coordinates. And we have observed that the same function have different u and v's in the case of Cartesian and polar coordinates. So here is the value of u and v in the case of Cartesian coordinates, and here are u and v in the case of polar coordinates. So remember, the function is the same, but if we change the coordinates from Cartesian to polar, the real and imaginary components of the function will be changed. Now let's consider some very special complex valued functions which are going to be part of our further discussions in complex analysis. So one of the famous example of such functions is polynomial function. So what is a polynomial function? A polynomial function is an expression of the form a naught plus a1z up to so on an minus 1 z raised to power n minus 1 plus an z raised to power n, where z is basically a variable and its values are coming from the domain of this polynomial, and these ai's, the coefficients of this polynomial, are complex numbers. Of course, the domain of this polynomial function is the whole complex plane. In other words, we can evaluate polynomial on any complex number from the complex plane. Now this an is the leading coefficient, and this n, which is the highest power in a polynomial, is the degree of the polynomial, which in this case is n. Now let's have a look at some special polynomials. So one of the special polynomial is linear polynomials. In other words, when the polynomial has degree n is equal to 1. Now these are called linear polynomials because the degree of z in this case is 1, and of course the coefficients are complex numbers. Now these polynomials have very interesting geometrical properties which we will see in our further discussions. Another example, so 1 plus z square. Of course, we can see that the coefficients are complex number and the variable is z, and so it is a polynomial function. Now let's have a look at another example where we have 1 plus z square plus z cube plus z raised to power 4 up to so on. So it's an ongoing process, and this function is not a polynomial. Why it is not a polynomial? Because polynomial is always finite sum of terms. Now in this case, the terms are not finite and it's an ongoing process, so it is not a polynomial. In fact, it is a series. Now let's have a look at another example where we have f of z is equal to 1 over z, or in other words we can say that this is z raised to power minus 1. Now also there is another condition on the polynomials, that the powers are always non-negative. So in this case the power of z is negative, so that's why it is not a polynomial function, but it's another kind of function. 1 over z, it's rational function. So what are rational functions? So rational functions are basically quotient of polynomials p of z over q of z, where p and q are polynomials. So they are polynomials possibly of different degrees. Now one of the special type of rational functions are linear fractional transformations, where the numerator is a linear function and the denominator is also a linear polynomial. Now in this case we impose some further conditions, ad minus bc, so that it has its inverses, and we will see these kind of transformations or functions in our further discussions. Once again, these functions have very interesting geometrical properties. Now sometimes we are given an expression which is not a function by definition of the function, but we can construct many functions from this expression, and of course we can use those functions to discuss the property of that given expression. For example, if we are given f of z is equal to z raised to power 1 by 2. Now we know that if we are calculating a square root of z, then we are going to have two answers. So in other words, we can say that if the input, if I let's say take input to be 1 plus iota, then the output is not going to be unique. I'm going to get two different answers. Okay, so the first root of 1 plus iota, and then we have second root of 1 plus iota. So if we say that this expression is a function, then what will be the problem? So the problem is input is a complex number, but the output is not unique. So unique means it should be exactly one output, and in this case we can see that input is a complex number, but the output is not a unique complex number. So there are two complex numbers as an output. So that's why this expression is not a function, but we can construct two different functions from this expression. So one of them is the positive root, and the second one is the negative root. And of course, if we are taking positive roots, then of course the answer is going to be unique, and if we are considering roots with the negative sign, then the answer is always going to be unique. So these two, f1 and f2, takes inputs as complex number and give us unique outputs. So that's why this f1 and f2 are complex valued functions. Now these kind of multi-valued functions appear many times in complex analysis. So one of the trick to deal with such functions is dividing them into many functions. Now in this part we studied how to write down complex valued function into real and imaginary parts. We also discussed some particular complex valued function, for example what are polynomials, what are rational functions, and we also saw what are multi-valued functions.